Well, thanks a lot. Well, first and foremost, thanks a lot to the organizers for putting together this nice event and giving me the opportunity to talk. It's going to be a simple talk based on this work with Balázs, who's going to talk later in the afternoon, and other collaborators, as well on some work in progress of mine. But well, before discussing physics, of course, a word on the man. We've seen this picture, right? Not very original. Is the sorry? Yeah, I'll come back to that. So the first one you get when you Google Hubert's name. It's quite old, as you say, 10 years almost. But I mean, he didn't change so much, except for one thing, of course. I had the privilege to do my PhD under the supervision of Hubert, actually under the supervision of Hubert and Jesper. And so let me take this opportunity to say something which hasn't been said before, and wish a happy birthday also to Jesper, who's turning 50 precisely today. And 50, would you believe that? If we look closely, you guys indeed do have some gray hair, and I'm sorry because I'm probably responsible for a bunch of them. To put things back in context, I started my PhD exactly 10 years ago. So that's me here in the large chronology of students Jesper and Hubert have had together. So I'm sorry for the earlier ones, in particular Yassine, and the newest ones, which I didn't put by just lack of space. But so the faces here, I mean, you might recognize most of them, right? And many are actually present at this conference. And another thing you might notice is that, until me, Jesper and Hubert used to assume one new student almost every year, while after me, they somehow felt like they had to take a 4 years break. And I think that says it all. I gave you guys a hard time. It took us a long time to have my first PhD paper out together. But through all this, Hubert and Jesper have been so patient and so supportive that I could never thank them enough. And especially Hubert, actually, what was I going to say? He's been really patient. And at that time, I guess I didn't really realize to its full extent how unrewarding that could be for him. But now I think I get a more precise idea because, little personal parenthesis, I just had a baby this summer, so I've spent the last few months, changing diapers. And I realized that might be quite close to what Hubert has been doing for me all those years. So, in retrospect, thanks, Hubert. So more seriously, a lot has been said already about Hubert. And I can only agree to that. His physical intuition is absolutely illuminating. It's been an honor and a privilege to work under his supervision. But maybe on a more personal note, what I'd like to pay tribute to here more specifically is how supportive and concerned Hubert has been with me and more generally, I guess, with all of his students. Hubert is really concerned. He's really concerned and supportive. He's really worrying about his students, and well, you all know Hubert, right? So he takes the art of worrying to a pretty high level. He has nights of insomnia because of his students. He also gets his hand dirty. With me, he just read through the piles of numerical nonsense I was sending him, and from there he was extracting, genius intuitions, which would guide us for months to come. So that was really precious. Sorry? Yeah. I didn't dare that. Where was I? He's putting a lot of time and energy into that. But what I'd like to finish with, and what struck me the most, maybe, is how Hubert was supportive to me, not only during my PhD, but also all the time after that. Because, well, quite frankly, I thought that once my PhD would be over, he would just, let me vanish because his job there was done, and also given the hard time I gave him, I thought that would also be fair that he just, would let me go. But the fact is he hasn't. I mean, he's been helping me so much and supporting me so much all through my postdocs and after that. And well, that sure has helped a lot, and also that has meant a lot to me. So well, for that and the rest, thanks again. And well, happy birthday again to the two of you. Okay, now some physics. So yeah, the title is Hard Road Spin Chains. And well, let me start by putting it in a like in the context of quantum integrable system. So what I'm going to be talking about kind of sits between what I would call the simplest quantum integrable models, namely non-interacting models, and complicated integrable models, namely interacting ones. So I mean, we had a really nice talk by Paul about free fermions. I mean, that's the canonical example I would take for a non-interacting model. So the XX chain here, which you can map onto Jordan-Wigner fermions. I mean, you can solve it really easily. You can compute a lot of stuff. And if you want to view it through scattering language, S-matrix language, or just beta ansatz, you have an S-matrix which is really simple. It's just -1 for any momentum. And at the other end of the spectrum, we have, so what I call complicated integrable models. So, I mean, the canonical example for me is the XXZ chain. And there, if you go back to the S-matrix, now it's going to be some function of the incoming momenta. And so what I'll be looking at is kind of in the middle between these two. And, okay, I'll argue why we might call that next to simplest integrable models. And these correspond to, between quotes, hard road deformations, which you can view as obtained from free models by just giving some width to the particles. So I'll detail this more later, but typically if you want to go back to S-matrix, the S-matrix now is not as simple as in a non-interactive model, but it's just a phase of this form. And well, if you, for instance, do some really simple Bethe-Ansatz calculation with an S-matrix of this kind, then you'll see that, for instance, it forbids particles to occupy neighboring sites. So it's what you would get, for instance, by taking some, I don't know, XX chain, but forbidding particles to sit on neighboring sites, so giving them a width of 2 sites. Okay, so these are typically the models I will consider. And, well, there are actually at least 2 motivations for that. And the first motivation, I mean, has been discussed a bit already in this conference. It comes from out of equilibrium dynamics. So as you know, there's been a huge activity in the community trying to use integrability to compute stuff out of equilibrium. One of the simplest setups is that of a so-called quantum quench. And so what you might want to compute is, for instance, the time evolution of some local observable here, starting from some initial state psi naught. And there are basically 2 main roads that you might want to follow to compute that. The first road is to just expand this over a complete basis of eigenstates. And well, this leads to the so-called quench action of JS and Fabian, which is really successful when you take the large T limit, and I mean, you can compute some saddle point evaluations, but it's fair to say, and Fabian already mentioned that in his talk yesterday, that it's really difficult to use this method to compute finite time dynamics, except in non-interacting models. Okay, so this is one way, and another way, which also actually Fabian mentioned yesterday, is to go through a transverse channel and use a so-called boundary quantum transfer matrix. So this is an original idea of Balázs Pozsgay, and then we continued that with Balázs himself and Lorenzo Piroli in a series of papers. And well, this method is really nice because you can really use it for truly interacting quantum systems, but it's also limited a bit because you can use it, for instance, to compute observables such as the so-called Loschmidt-Echo, or return probability. But when you turn to really the dynamics of local observables, once again, you're stuck. I mean, you have some really heavy Bethe-Ansatz machinery, which is perhaps doable, but seems really, really difficult. So yeah, these 2 approaches have been stuck with interacting models, and it's quite fair to say that most exciting results that came lately have actually used models which are a bit different, and rather than traditional Bethe-Ansatz, they've used tensor network techniques. And the models are not exactly the good old XXZ spin chain we're used to, rather discretized time evolution or unitary circuits. And so let me mention these papers here by Katia Klobas, Bruno Bertini, and Lorenzo Piroli, and also another one with Ignacio Sirac and Tomasz Prozen. There were some nice calculations of time evolution of local observables. And well, to give an illustration of the kind of models that they considered, let me present the most famous and probably the simplest of them, which is the so-called Roof 54 cellular automaton, which is so simple that, it's been also, sometimes advertised as the simplest interacting integrable model. You might argue about that, but there's the point there. So the model is really simple. Initially it's just a classical deterministic, but you can also view it as a quantum model. So you have degrees of freedom which lives on faces of some square lattice. So the faces are either occupied or empty. And so occupied is black here, for instance. And so what you see is that when you time evolve, you have some left movers, right movers, which just propagate freely until they meet. And when they meet, they scatter with some time delay. So you see here it's you see it's really close in spirit to what I was mentioning before with hard rod deformations, except that here strictly this would correspond to a hard rod of negative length, but the formalism is really the same. And so this model has been studied in a variety of papers. I also forgot to mention a paper by Jérôme here with Vincenzo Alba and Marco Benegnac. So it's been there has been some interest in this model and some interest in understanding what are the integrability properties of such models. Okay, so that's one source of interest. And another one comes from a different field, which is that of TT bar deformations of integrable QFT. So I'll say really little about that because I'm definitely not an expert, and also there was a talk by John Carty on the subject. What matters to us is that recently, there have been two papers, one by John Carty and Ben Doyon, another one by Marco Medegnac, Giuseppe Policastro, and Tagato Yoshimura. And among the many results in these papers, one common result that they have is that you can interpret TT bar deformations as giving some width to the particles in your theory. There is some slight subtlety. The width here depends on the momentum of the particles, but you can actually consider another family of TT bar-like deformations. So that was also tackled in the paper by John Carty and Ben Doyon. So these simpler deformations, instead of being constructed on the conserved energy and momentum, they're constructed on the momentum and particle number. And there you see that the S matrix now becomes deformed as follows. And so this is exactly similar to what I was mentioning before. So now the interpretation of these deformations is really that they give a finite width to particles. So that's another source of interest for all of these hard rod-like models. And well, before going into our work, really let me just give a brief overview of the state of the art, because there have been actually around models which are or resemble hard rod deformations for quite a long time. So maybe the oldest one, I'm not even sure, but I guess it's this Bariev model, which you see, it's like an XX Hamiltonian, except it's with, between, the jumps are between next to nearest neighbors, and the jumps are controlled by, each time the spin which is in the middle. So in particular for this parameter u being equal to plus or minus 1, then, you can convince yourselves that this really becomes equivalent to some hard rod deformation. If you're not, I will go back to this in a bit. You also have some hardcore fermion models which were studied by Paul and Nienhuis and Schoutens, mostly for their supersymmetric properties. You also have, and we'll see that model again, the constrained XXZ model by Alcaraz and Lachaud, which is really analogous to XXZ, except that you have the constraint that you cannot have you cannot have two downspins less than L sites apart. So it's a generalization of XXZ where now you give some width to the downspin somehow. And you also have another model called the phase model by Pozsgay and Eisler. And you probably have many more models around. The point here is that, so yeah, these models were here, but it's not really clear what is the integrable structure behind them and how you construct them in general. So that's partly what I want to approach here in this talk. So here's the outline of what I'm going to discuss now. So there's going to be two parts. First, I'm going to discuss a model which is the so-called folded XXZ model, which, well, we discovered, between quotes, I'll explain, with this work with Balázs and collaborators. And actually, after that, we found out that, well, it has been just discovered before in another nice series of papers by Maurizio, Fagotti, Lennart, Zadnik. He was here, and Kemal, who's here. So yeah, so what we did was actually not so different from what they did like 1 year before. And even before them, actually, the model I'm going to present was was seen in another papers from another community, and for different reasons. So yeah, it's been a model which has been around for a bit, but so the perspective I'll present here is a bit new, so well, worth mentioning in any case. And then I'll move on to what's more work in progress, and I'll be really quick on that, namely the possibility to geometrically and systematically construct hard rod deformations from known integrable models. Okay, so first, so the folded XXZ model, and the name, by the way, comes from the paper of Maurizio and collaborators. So the construction is really simple. So you probably all know the XXZ model. It's part of a big family of commuting charges. So I wrote here the XXZ Hamiltonian as Q2, just to remind that it's part of a big family. So all of these charges, they're mutually commuting, and they're polynomials in delta. So it's easy to convince yourselves that if you take the leading delta behavior of all of these terms, you'll end up with another family of commuting charges, right? So that's what we do here. We take the leading terms in delta, well, you see that the XXZ Hamiltonian now it becomes something non-dynamical, so it's really some classical Ising chain. So we define as a new Hamiltonian the first really dynamical charge, which is also even under parity, so not this one, which is odd under parity, but this one. And so what we define as the folded XXZ Hamiltonian is this object here. So the way it acts, you can just read off from here, but maybe it's clearer here in pictures. You have some exchange between neighboring spins of opposite sign, if and only if the two surrounding spins have the same orientation. Otherwise, you have nothing happening. And, well, maybe it's clearer to see this in another formulation of the model, which is a dual formulation where we now put degrees of freedom on bonds. So we draw a particle on a bond whenever the two neighboring spins have opposite orientations, and if the two have the same orientation, we just draw no particle, so an empty dot here. So in this language, the mapping is exact up to subtleties with the parity boundary conditions, but I won't bother with these here. I'll really consider these new objects here as my new model. And so in this bond language, well, you see that Q2 becomes just the density of domain walls. And Q3 and Q4 generate some dynamics on the domain walls, which can be summarized as follows. Isolated domain walls don't move, but whenever you have a pair of domain walls, then they can move right and left. So to illustrate this, let me just show some configurations of the system at different times, and so between different lines you have actions of the Hamiltonian. So you see that pairs of domain walls they can move either right or left. They can do whatever. While isolated domain walls, they don't move, except when they scatter with a pair of domain walls, then they get shifted by 2 units. Okay, so through this evolution, the number of isolated domain walls and the number of pairs of domain walls are both fixed, so we can work in different sectors. And in particular, in the sector without any isolated domain wall, the model is equivalent to precisely the constrained XX model I was mentioning before, namely the delta equals to 0, particular case of the Alcaraz-Lasso model I mentioned before. Or another way to say it, this model can be obtained from the XX model through the following mapping. You just map a spin up to an empty particle and a spin down to a pair of particles. Okay, so that's for the sector without any domain wall, sorry, without any isolated domain walls. But now if you want to view the full Hamiltonian, it also actually corresponds, I mean, you can map it to a known integrable model, which is a kind of generalization of the XX model, and which is the so-called SU3 XX model of Massarani and Mathieu. Okay, but we don't use that so much in practice, it's just by curiosity. Okay, just, well, it's useful, it's instructive to see how the physics I just mentioned comes up in the Bethe-Ansatz language. So, a real quick reminder on the Bethe-Ansatz for XXZ. You know that, okay, so here I'm parameterizing delta as cos eta. So you know well that Bethe roots typically organize themselves into strings. An n string is typically interpreted as some wave packets of n bound up spins, and as you increase delta, the wave packet becomes more and more tight. So we know how to express the eigenvalues of the various charges carried by the various types of strings, right? And we also know how to write the scattering between strings of different types. Okay, so I won't detail that here. And so now, well, when we take the delta goes to infinity limit, which was actually already considered for different reasons in this paper by Bogoliubov and Malishev. Well, as I was telling you, strings become more and more bound. So in the delta goes to infinity limit, an n string becomes strictly a packet of n consecutive down spins in a sea of up spins. Oops, okay, so here, my drawing is the opposite, sorry. And so if you go back to the bond picture, then this means that an n string is equivalent to 2 domain walls at distance n. So what this will mean is that, well, you expect that one string, which is a pair of domain walls, without any particle, which is, yeah, a pair of domain walls, will have some dynamics, while higher strings won't have any dynamics. And this is indeed what you see when you take the limit of the various charges. So as expected, Q2 is just 2 for any type of string, so it just counts indeed the density of domain walls. But now Q4, which is the energy of our model, it has this expression here for one string, while it's 0 for higher strings. So really higher strings don't bring any contribution to the energy. And well, you can also compute the scattering between strings. So you get these expressions here, which become indeed phases, as I advertised before. So I won't go into the detail of the Bethe-Ansatz, but what you see is that all the detailed information on higher strings, namely higher than 2, disappears from the Bethe-Ansatz. Only what matters is the total number of those strings and their total momentum. Okay, so to finish with this model, a few more funny aspects about it, which we explored a bit, but I won't detail. Yeah, so one fancy word, the fact that domain walls don't move when they're isolated, but move only by pairs, is reminiscent of what people have been called fractonic dynamics, and it's been a pretty fashionable topic. Another aspect which relates to what I was mentioning in the beginning is that this model has a solvable quench dynamics. We can compute exactly the evolution of some observables. So in particular here we computed one example of emptiness formation probability starting from a given initial state, and so you get an exact formula from there. And the third aspect is Hilbert space fragmentation, and this is something we've seen already yesterday in Fabian's talk. Namely, you see that, well, isolated domain walls, they split the Hilbert space into different sectors which just don't speak to each other, right? And these sectors, they're characterized by configuration of isolated domain walls at a given distance from one another. Well, to make it clearer, in case it's not, here I'm giving an example of various configuration for a system of, I don't know, 10-ish sites. So here I have various states which are connected to each other by the Hamiltonian. But between two boxes, the Hamiltonian doesn't have any transition. So as a result, what you have in the spectrum of your model is exact degeneracies whose number increases exponentially in the system size. And so that's, well, pretty interesting for several reasons. And also that connects with other aspects which have been investigated. OK, so I think that's it for folded XXZ model. And now, really briefly, let me sketch some speculations about geometric construction of hard rod deformations. And so before that, let me just mention something which actually I think Balázs will discuss a bit in his talk, so I'll be real quick on that. The so-called hard rod XXZ model, which is just a generalization of the model I just presented to you to non-zero delta. So you see this part is what I just discussed, and here you have some non-zero delta term. So yeah, as I was just mentioning, this extends folded XXZ in the bone representation to delta non-zero. In the sector without isolated domain walls, this corresponds to the constrained XXZ model of Alcaraz and Lachaud. And so, well, Balázs and collaborators came out with this model, showed it was integrable, and in particular devised a Lax operator for it. And this Lax operator is based on a pair of two-dimensional auxiliary space. So it has this structure here. So you see that depending on whether one of the auxiliary space is occupied or not, you have different types of interactions. So here is just a trivial translation, and here you have the usual XXZ Lax operator. So it's kind of mysterious, this Lax operator, and they found from there an RTT or RLL equation with a trigonometric R matrix, which is not of the difference form. And yeah, so that is the starting point I had, thinking that, yeah, I mean, that felt a bit unnatural. I mean, I kind of want to understand this in a more systematic manner. And well, I'll be really, really quick because it's also really work in progress. But so here's a sketch for a geometric construction of hard rod deformations, starting from a given integrable model. So let's take the example of the 6-vertex model. So you can write the configurations of arrows as follows, but you can also represent them by putting occupied edges on down-going or left-going arrows. So you have associated weights here. So here you have a configuration of the 6-vertex model on a strip. And so starting from there, I'm going to, as a first step, reinterpret the lines here are as jumps between heights on a 3D surface. Okay, so that's just just a geometrical transformation. But now, imagining this as a 3D surface, I can tilt it in various directions. And tilting it in various directions, I can give arbitrary width to these lines here. And so, well, let me give you the example here of L equals to 2. So we take a very anisotropic limit. And now we'll take what happens on a line here to be our new transfer matrix. So to encode this in a usual transfer matrix language, I actually need to introduce two lines. So that's where it gets a bit dirty, and I hope I'll be able to render this a bit more slick in the future, but so far it works. Anyways, so yeah, I mean, I generate what I just drew before as, from a transfer matrix with two rows. I put the original blue lines here in full lines here and dashed just to distinguish them. And well, I'm almost there because now I have these, bended lines which I don't like. So to recover some more usual row-to-row transfer matrix formulation, I'm just going to compose this with, I'm almost finished, with a one-side timed translation. And so I recover something like this. And now I remember the local weights I had from the XXZ model, and I encode them here using the following rules, that interaction weights are carried only by full lines, while dashed lines just jump through, and they don't give any interaction. Okay, so that's ugly, but that turns out to kind of recover the lax operator by Balázs and collaborators. Actually, almost, because here you see that I'm not allowing for isolated particles. So, I mean, that is something I have to fix a bit. But still, I mean, we have a lax operator whose structure is really analogous to that I presented earlier. In the sector with no isolated domain walls, actually, it recovers the lax operator of Pozsgay and collaborators. It has some RTT equation with an R matrix, which is much similar to that they derived. Yeah, so things I have in progress is try to interpret, okay, I start with this one, to interpret the model with isolated domain walls. So the full model of Balázs and collaborators as a decoration of the present one. And also what I would like to be able to do is to interpret the R matrix here, which is not of the product form and which is a bit cryptic so far, as a two-line R matrix, like which would, you know, write as a product of four R matrix, all of a difference form. Okay, that brings me to my conclusions. So, well, we've seen the folded XXZ model, which appears naturally as a delta goes to infinity limit of XXZ and has many nice features, so I won't enumerate them anymore. And my main interest was to try to, you know, systematically construct hardware deformations. So from what I've shown you, I mean, we're able to recover the constrained XXZ models of Alcaraz and Laszlo. So no new models so far, except that with my construction, well, you could also derive models with L negative, and you can also extend that to many other models, like, I don't know, start from SU3 or stuff like that. But maybe more, what's more interesting is that there's probably much more to be understood. I mean, the structure of the R matrix and so on. Even though, I mean, I take seriously a lesson from Paul's talk that, I mean, we need to stop being, no, but really, I mean, we should stop being obsessed about writing everything in the RTT form. So maybe it's, yeah, there's some slicker reason for integrability here, which so far I haven't figured out, but that's, yeah, some ongoing work. Okay, with that, well, let me thank everyone again, and well, happy birthday, Hubert and Jesper.
Yes, a question from Jesper.
Okay. Well, I asked my question, I might as well show this. So you mentioned in the beginning that this rule 54 stuff corresponded to having a negative length. Could you explain that?
If okay, imagine just a model of free non-interacting particles. So when they cross, they just don't scatter, right? Okay, can you see me? Now, if you give them a finite width, when they interact, they will just, you know, bounce against each other. So you will have some, you know, they will be accelerated here. While if they have some negative length, then they will be delayed when crossing. You know, it's like attractive vs repulsive interaction. And in rule 54, I don't know if you remember, but the scattering that you had was precisely some time delay when particles cross. So that's why you might want to interpret that as a negative length.
Something that always puzzled me a bit for rule 54 is that this model is completely deterministic. If I tell you what configuration I want in the lower row, it's going to produce just a unique configuration in the upper row. Mm-hmm. But usually when I think of statistical models that are integrable, they don't work like that. There are several possibilities for what will happen later. The transfer matrix has a lot of non-zero elements. So why is this? How can you reconcile this?
Well, okay. Well, two things. Indeed, it's probably like way too much machinery to try to reinterpret that as an integrable model as we are used to. And probably it's stupid. But since, I mean, we're into integrable models, we kind of want to relate to two things. But if you want to relate that to usual integrable models, I think that this will be the hardware deformation of the stupidest integrable model you might imagine, namely just braid, you know, particle crossing each other, and that is not also in the models we're used to is deterministic. Now, second thing, even though it's deterministic, the reason it's interesting is that, well, it has many of the features that you would expect from an interacting quantum many-body models, namely, so I don't know, Prosen and collaborators and many other people did hydrodynamics, for instance, on that, or computed quenches and GG, and you see that it has all the features that you would expect, namely ballistic plus diffusive corrections. It has, you know, thermalization. I mean, not thermalization, but generalized Gibbs ensemble. So it really does have the features. Even though I agree. I mean, it's yeah, it's too simple. Yeah.
Hey, I would like to ask about your ansatz for folded model.
About, sorry?
Your ansatz for folded model.
You mean the
So
beta ansatz?
Yeah, beta ansatz. So, can you comment on the completeness of this ansatz? Are you sure you obtain?
Well, okay. First, no, I haven't. I cannot comment. I haven't wondered, but I bet it should be complete. I don't know if. Sorry. No, I bet it should be complete, but it's just. I mean, in different sectors. Sorry. Oh, what would I bet? Oh, my lunch. Yeah. I mean, it's like free fermions in different sectors. So I guess it shouldn't get any more complicated than that. But I mean, you're even more expert than me on this, so perhaps you have a different opinion.
Okay, because of the number of particle types, just.
Oh yeah.
I mean, do you have some problems like the boundaries?
Yeah. No. Oh, okay. I've been overlooking in this talk, and also, I mean, in all I've done with this paper, the what happens at the boundary. And yeah, sure, you have subtleties at the boundaries, and okay, indeed, they might spoil completeness, but really I haven't thought about that.
Okay, thanks.
Okay, so I propose that we. Okay. Yeah. Sorry.
Yeah, hi, Eric.
Hi.
I just had a curiosity. So, in my understanding of hard rods, the original ones, let's say, of Herwig-Spong, when I try to compare that to a quantum system, the way I think of it is that in the hard rods is, well, especially the effective velocity equation for hard rods is exactly like for an integral model, but with a scattering phase that is just a constant. So is that the sense in which these are hard rods as well in this model?
Yeah, I guess you might. You might view that as just some lattice modelization of, you know, the scattering you would have between rods and stuff like that. But it's just a name. It's just, you know. Yeah, maybe that's an abuse of name, but the idea is just, yeah, you started from models where you have particles, and now you give these particles a width, and you impose hardcore constraints like that, yeah, doesn't.
Okay, so Hubert, you wanted to ask a question? Okay, so I propose that we continue. I have plenty of questions, but I will ask them.
So do I have my lunch finally, or?
I'm not going to bet my lunch on with you. So okay, let's thank Eric again.